fundamentally, Fluence is a is a permissionless and secure peer-to-peer protocol, where the protocol is primarily exclusively focused on compute. And with that, we have a peer-to-peer network and a whole bunch of open source tooling, and we'll go through all that. So why do you want a permissionless, secure peer-to-peer protocol that focuses on compute? Well, it's for several reasons. One is that you can really improve users' control over their own data, and you can massively improve your control or exposure to control and getting autonomous participation, even anonymous or at least pseudo-anonymous participation in a large network. And that is increasingly desirable. How is that different right up front? How is it different from blockchain? One of the key differences is that in the blockchain, every node reruns every computation that's been done. That's how you consensus, that's how you build blocks. In the Fluent peer-to-peer network, this is not the case. Nodes are independent, and they can join, they can leave, and because of that, it's particularly in comparison to blockchain, it's highly scalable. However, we have something that gives you a degree of determinism. We'll get to it a little bit later, which is the result of the way we process workflow and data in the network. So what do you have in the network? In the network, you have a bunch of nodes, and then on these nodes, you can actually deploy services. So a node operator doesn't necessarily have to be a service developer or an application developer. And the way you deploy services on these nodes is you basically create WebAssembly IT modules. That's different from BindGen, by the way. So WebAssembly interface types are sort of the backend WebAssembly. It runs in the browser with some help, and we have a Marine runtime. We call it Marine. It's we'll get into a little bit later, and it's built on top of Wasmer. And from that, you can run these highly portable WebAssembly modules. And what you end up doing is you create these WebAssembly modules, and then you logically construct them into linked services. So the service is a logical structure consisting of one or more WebAssembly modules. And at the compile time, they're shared nothing between those modules, and you link them at runtime essentially. And even though WebAssembly IT is or WASI-32 is highly sandboxed, there is a way actually to execute external effects from those modules. So you can download, upload, modify, replicate. You can do a whole bunch of things that may or may not involve interacting with the node. And as you see on the right, we have a little bit of network outline. You can actually integrate with services that are not deployed directly on the peer-to-peer network itself. So the way you do it is you write WebAssembly app adapters, and then you can start composing over those third-party or out-of-network services. And you can do this with Aqua. And this is sort of Aqua is we'll get into it a bit. So since Fluence focuses on compute, the developer are fundamentally tasked with bringing store. And store, of course, is super important. And we offer a limited store capability through file store, or actually SQLite is available as a WebAssembly module. But for serious storage, you may want to look, particularly if you're in the decentralized world of applications, you definitely want to look at IPFS or Arweave or something like that. And this is fully possible. And this is what we're going to look at a little bit today. Now, it's a relatively small group. And so what we can do is we can make it relatively interactive if you want. So if you have any questions, just let me know, and we'll try to get into it rather than wait till the end. All right, why is this not? I'm like totally frozen. Okay. All right. So in order to participate in a general purpose peer-to-peer network, you need tooling. And one of the reasons you need tooling is that you want to change your request response model very significantly. In a traditional client server model, what you do is you do a request, you get a response back to the client, then you do something with that response, and then you have another request. So for example, if I had to do a credit card authorization, and I wanted to tell my customer SMS what the result of that authorization was, in a traditional client server model, I would go and call, I don't know, I call out to Stripe, I do the authorization, I get the result back to the client, and then I call on, I don't know, Twilio to send an SMS to the customer. So that's request, response, request, response. In a peer-to-peer network, what that offers you is an alternative model. In a peer-to-peer network, what you can do is you can, the way the services are hosted, you could, assuming we use the same model and we have those WebAssembly modules in place that wrap Stripe and Twilio, we could call Stripe, then directly move that result forward to the SMS service, and then at the end we close the loop. And that's a very, very different load on your client. So peer-to-peer models really offload a lot of the work and the interactivity between the client and the services. And that allows users to really take control of that data, eliminate those centralized intermediaries we briefly referred to before. And what's super important, or could be super important, is enable really thin clients. So edge devices. I mean, I'm looking here at my phone. It's a big old, I don't know, big old Pixel, you know, with like tons of features and power, and my laptop. But for the majority of the 8 billion people out there, most of the devices are much thinner, much less powerful, and this is where a lot of the compute can be provided by offloading it to the network. And that's where you need the tooling. And we have a tool stack called Aquamarine, and it's comprised of Aqua, which is a language that's purpose-built to program distributed, in particular, peer-to-peer systems, and Marine, which is the WebAssembly runtime. So if you go back to this diagram we looked at before, on the right, the green things could be our clients, which could be a browser, and then you have the nodes, and then on each of the nodes you have services, where the relay, by the way, if you're not a peer-to-peer specialist, a relay is a node in a peer-to-peer network that is publicly accessible, as opposed to some nodes that may be behind a NAT. And the other thing is where you need relay nodes that are publicly accessible. If you're building applications from your browser, the browser can't directly connect to the network. It has to go through a relay. So that's what we're doing here. And so every node has that Marine stack, and that allows you to basically distribute your composition separately from your business logic, and basically lets you build peer-to-peer applications. There is an added benefit, which basically, if you're into zero trust frameworks and zero trust networks, basically trust nothing at any given time. The way the communication of results, and it's actually called a particle or a smart packet, but which is the little green thing on the arc. At every peer, at every service, at the ingress and egress, there are signatures happening, and this allows you to basically verify your entire compute through the life cycle of the workflow. And let me go straight to Aqua. Aqua is a purpose-built distributed peer-to-peer programming language, which we developed here at Fluence. So why do you need another programming language? If you go back to this little diagram on the right, so you got your nodes, you got your clients, and you got your services on those nodes. How do you actually use them? And if you look at it from a blockchain perspective, the majority of the interaction comes from JSON RPC. But this is a general purpose network. And we have no idea what what kind of services you want to deploy on that network, on which nodes and which subsections of the network. So you need a way to harness those services, to find them without having to know everything about the network. And this is where Aqua comes in. Aqua basically lets you program network itself, the nodes, and through that the network, and compose these decentralized applications from those services you've seen on the right here. And we believe it's gonna commoditize peer-to-peer programming because it is actually super simple. I should do a show of hand, but it's probably, how many of you have ever programmed at the lib peer-to-peer, lib P2P level? Okay. Most people today who are exposed to distributed programming, in particular peer-to-peer programming, is actually at the blockchain level, right? Almost all blockchains use some sort of peer-to-peer protocol to communicate amongst themselves. But all this is abstracted through a single node access and CLI tools or higher level tools from the user. You don't have to do anything. But if you look at most of the core development around node communication, any one of blockchain projects, it's huge. It's a huge part of the programming effort. It's a huge part of the break effort, and this is for fundamentally single purpose nodes, right? Single purpose application. I mean, the application is the blockchain, which may include the EVM, which then executes whatever program you want. But from a peer-to-peer perspective, it's a very nice vertical stack. And it's still, the point is, it's peer-to-peer programming is challenging, and we want to take the challenge out of it. And that's where Aqua is going to come in. Just real quick on Marine. Marine is you don't necessarily see it, but it runs on every node and it executes those WebAssembly modules. However, in order to write those WebAssembly modules, right now you have to do it in Rust. It's a subset of Rust, and we've extended the Rust compiler, Cargo particularly, with Marine necessary extensions, so we actually get the compile target we need, which is WASI 32. However, it's standalone. Oh, by the way, all our tools, everything is total open source. It's either MIT or Apache 2, so there's nothing preventing you from mix and match whatever you want to do, running nodes, rebuild nodes, whatever it is. So Aqua is our entry for most developers into peer-to-peer programming. So if we go back to the example I just gave with, say, Stripe and the SMS message, what we would have is we have an adapter or a service that does the credit card authorization, and we've got a service that does the SMS notification. And now we know we have that service, and that service may be running on one or more nodes simultaneously. So depending on your fault tolerance you want in your application. And that's where Aqua comes in. So if you look at the bottom here, oh my, okay, cursor's back. This is sort of a very simple but fancy hello world in Aqua. So assume for a minute we have a service out there deployed, and it's a greeting service, and that greeting service takes two variables, string and a boolean. And basically, depending on the boolean, the greeting service, the hello world service, either says hi Berkeley, or if it's false, bye Berkeley. This is what we have. This is our fancy hello world. It says either hi, whatever the name string is, or bye, based on that boolean. So in Aqua, this is actually Aqua code. We create an interface called greeting service that takes a service ID. Now, a service ID is a unique identifier. Think of it as a UID that is the result of deploying WebAssembly modules, one or more, with linking instructions on a node. And this is all we need once we know the node we're on. And then within that interface, we basically have a greeting. And as I just said, it takes its two variables and returns a string. So in many respects, you can, since you're a blockchain cohort, you can think of it as an API, right? I mean, this is your binding to the service already. Now from line 4 down, this is the actual Aqua function that makes something happen, okay, with that greeting service. So we call that function greeting. We get this name. This is the string right here. We get greet, yes or no, is a Boolean. And now we have a node. Node, which is a string, is the peer ID of that node in the net. And we have a greeting service ID, which is also a string, which is that service ID, which is the unique identifier of the greeting service. So basically the node plus the greeting service ID give you a location addressable tuple. And this is, as a user, as a developer, this is all you need. And this is actually like really, really cool. So basically what we're seeing here in the greeting function, we basically say on this node, which we defined here, on that peer, and this is where underneath is the Aqua virtual machine, and some lib P2P work basically gets you there. You don't have to do anything in terms of routing other than specify your point of interaction, which is that particular peer. And now we instantiate that binding with that greeting, with that ID from here to here. So now we have a instantiated interface greeting service on this particular node, and we can do something with it. And what we do with it, we basically call that function greeting, our hello world, with that name and that Boolean. And that gives us the result, and then we return the result back to the client. Now, so there's two results. This result actually collects that string coming from here on that particular node, and this down does, it actually returns the result to the client. And there could be a relay node in between, whatever. You don't have to worry about it as a developer, you just get it right back. Any questions so far? Okay, I see. Okay, hang on. What's the package ecosystem look like for Aqua? Is it interoperable, say, with Cargo or NPM modules? Okay, good question. Aqua and the actual WebAssembly modules have nothing to do with each other than that you use Aqua to orchestrate or compose services we get from WebAssembly modules into an application. The packaging for the WebAssembly modules right now is basically, we have a marketplace for it. It's not fully done, but it will be, I don't know, it's going to be like craze.io, but it could be there. We would like it to go there. So right now it's very loose. That's one of the parts where we haven't made as much progress as we wanted, because we're still like pushing the Cortec really, really hard. There's and hackathons around it, but that's certainly on the roadmap. So that's a good question, because in these, at the lowest level, a distributed service could be nothing but, and I don't mean this in the derogative manner, nothing but a function as a service. Your service could be an add function, add XY, that's it. That's the whole service. Or your hello world, that's the whole service. In other cases, you may have what could be a not so fine-grained service, like, I don't know, let's call it a fat service, where, for example, you port a Ethereum signing library or a Web3 library as a complete service package into WebAssembly, or libsec P254 56K1, for example. Then you have a much fatter service, and managing the services both from a distribution perspective, which was the question, is important. But the accompanying issue is, how do you discover those throughout the network and without having to know everything at all times at any given time? And I don't know if we're going to have time for that, but today, but we basically use DHT, and we've also wrapped that into Aqua, so we have a seamless programming interface. And we also have something that's coming online right now, which is called Trust Graph, which basically allows you to subjectively weigh trust in nodes, but also in applications and services. Very, very close. So there's most of the code is done. We just gotta build out a few of the behavioral layers. Okay, so how does this all work? We saw the little network, we saw those services, and I told you don't have to bring the result of each computation back to the client. And the way this works is called with what we call a particle. You can also think of it as a smart package, basically. So particles are conflict replication data structures that combine data and execution sequence and some metadata. So what's the data? Let's just say we look at our very simple greeting service. So our starting data would be the name, the Boolean, the node ID, the peer ID, and the service ID. And then we compile this Aqua into an intermediary language. We call it AIR, Aqua Intermediate Representation. It's not bytecode, but you can think of it as bytecode. It's just an intermediary representation. Very Lispish, actually. And when you create your application at a client, be it a browser, JavaScript client, whatever, basically what you're doing is you're creating this Genesis particle, and you literally are flinging it onto the network through a relay node, for example. So what happens is you have this, you have the initial data, your Genesis data, and you have your workflow. So you create this package, this smart package, and you fling it onto the network, a relay node, for example, and there it goes to the Aqua virtual machine. And the virtual machine now checks what's the execution flow, or are we in execution, and then looks on this node, do we have this particular service? If not, if this is not the wrong node, it forwards it to the right node, and that's where the service now gets called on the Marine stack. This is where Marine comes in, and the various WebAssembly modules comprising the service are executed, and now the particle, this conflict-free replication data structure, gets updated. And Aqua works both in sequence and in parallel, so there's an eventual consistency there. And a lot of signing at ingress and egress of the processing takes place, which brings you actually really, really high level of security. And if you recall at the beginning, I said a blockchain, every node reruns everything, which is sort of the limitation and the scaling issue with blockchains, right? And I said we're not doing this. So the difference, of course, is we don't have consensus in this sense on a service, but the way a particle is structured and the way signatures are happening along the computation arc, if you will, or route, you basically have a deterministic data and execution structure particle that you can rerun and check whether or not it's been done properly and signed properly. And so the rerunning of the compute is possible at the client level. It's not happening at the network level. So what you could do is you could write your own consensus layer, for example, which we have, by the way, we have a bunch of hackathons coming up. If anybody is interested, reach out. So if you wanted to build a consensus layer around your compute, what you could do is you could literally write services that now take that particle and rerun it to ascertain that it's been correct. And if you, depending, so I mean, there are different consensus methodologies you could use in algorithms, but you basically build services to check the accuracy of the services, and you can rerun that and build consensus around it. We can oracleize it, or you could literally go like with Raft, for example, or something like that in terms of service allocation, and use that trust graph structure I told you about, and build consensus layers on top of the Fluence network, whichever way you want. So if that interests anybody, as I said, we got some hackathons going on, or even if you just generally interested, we'd love to talk to you. Okay, so that was the particle. Any questions on particles? I take this as a resounding no. All right, let's move on. So finally, we're getting to our use case here. And the use case is how to use compute with store. And we want to use store with IPFS. IPFS, I presume everybody is familiar with IPFS. And Filecoin Protocol Labs basically is a peer-to-peer network that allows you to store and in content addressable manner. And this is obviously super cool because all you need is the CID, the content ID, and look things up. All right, now I need to switch to okay. So I got a bunch of code, and I can give you, and I want to run a demo. If it's, you just got to tell me what you want in terms of where you get the most value from the presentation. But let me just start with going through a little bit of code and as part of the demo. So what we're trying to build here is the following. We want to use IPFS as a decentralized store layer, and we want to store the WebAssembly module, or a WebAssembly module that makes up a service on IPFS. So I could just, so in the traditional workflow, or one possible workflow to deploy a service onto the Fluence network is you write your WebAssembly code in Rust. You upload that, you compile it into WASI-32 modules, and then you upload that module with some information, some metadata to the network, to a particular node where a service gets instantiated. And what you get back is basically a service ID, and you know which node you deploy to. So that goes you back to that peer ID and the service ID you needed. That's on your local machine. Another way, of course, is one of the reasons you do like to use WebAssembly modules is about the portability and the ensuing reuse, particularly in the open source community. So an alternative is to just say, you know what, I'm going to publish my package, my WebAssembly module in this case, onto IPFS, and now I want to deploy the service from IPFS. So let's build a module we can actually use as a service. And this is a super simple service. Basically, what we're doing is we're creating a service that calculates the file size. So if you look at, hopefully it's big enough, let me make this a little bit bigger. So this is the Rust code we compile into a WebAssembly module that we want to deploy onto a node or more nodes, and basically use it to calculate the file size. And if you look at it, it's basically this. Okay, I said everything needs to be written in Rust, and that's true, but the subset of Rust we're using is very, very simple. So do not be intimidated if you are by any chance by Rust. Some people are, because the subset of Rust necessary to write WebAssembly code is actually the easy part of Rust, and it's very similar to most languages. And the reason it's the easy part is because you don't need lifetimes, you don't need generics, you don't need any of that, because in WebAssembly everything gets passed by value. So it's sort of really the Rust fundamentals, no bells and whistles of it at all. And most people who look at it for the first time, who have background in JavaScript, particularly TypeScript, are usually get pretty productive in a very short period of time. So the big thing, so basically for the non-rusters, basically here we're gonna calculate the file size. So we have file path, and we get a result, which is this structure, what we call in Rust, or you can think of it as an interface, which has the size and the success and failure. Now, there's a little bit of a trick, it's not trickery, but circumvention of the way Rust works. In Rust, you have this built-in structure called the result, and we can use it because the only interface types we can use are the ones that are part of the WebAssembly IT specification, and the Rust result interface or structure is not. So we have to create our own. And so basically here, it's just, you know, same like you do it almost everywhere. You read the file, you get the bytes, you get the length of the bytes, and then you return the result. And the only different part for most of it is that marine macro. And basically what it does, it enforces the interface types that are available and usable in the program, and it adds some additional information from a compile side to actually end up with a WASI-32 target, because obviously that's what we want, because we want the WebAssembly module coming out of it. And that's really the big part in writing those WebAssembly modules, literally around that. And an additional result of using that macro is that everything that's marked up marine with the marine macro basically is a exposed callable interface type. So now let's just see. Okay, we are here. This was in service. Okay, so I obviously pre-compiled it already because it takes some time, and we have a build script for this, and basically this is what's important. So basically what we're doing here, and when we build this, is we basically, instead of cargo build release, we use marine build release, and that's just really the extension that gives us the WebAssembly module. And then all this down there is basically what we're trying to do is we basically say, you know what, we don't want that WebAssembly module only in the Rust scaffold directory structure, which is basically target blah 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 WASI-32. We want it in a directory called artifacts, and here it is. And then we want to do one more thing, and we basically want to export the interface types into another file, into an Aqua file. So as part of Marine, we have a REPL that allows you to interact with those WebAssembly modules locally before you deploy them. And if you look what we exposed here with those marine macros, so we have that interface, we have that function, we have that interface, and we have that function. That's it. And so Walt here, for example, is not exported. If you look at it, here, let me make this bigger for you. We have the right result, which is here. Yes, it's marked up. We got size result. Yep, got that. And we have the calculation of, we have two functions, write file and file size. And then if you want, you can run it and interact with it locally. You also have, which is not part of the code here, we've extended cargo to let you run unit tests on your WebAssembly module. And it was actually a tricky task, and Mike did it and extremely well, because here's the following. If you ran your regular unit test on this code, this is what you would be testing, but that's not what you want to test. What you really want to test is the WebAssembly module. So what we did is we built this extension that allows you to run unit tests on the WebAssembly module. And if you're interested, there's a lot of examples in our examples repo. It's github.com/Fluence lab/examples. There's tons of them. And if anybody's interested in it and we have time, I'll go through it. Okay, so we get the REPL, and let's have a look at Aqua real quick. So what we did is we basically, okay, let me just show you what we did. Artifacts. What was it called? There it is. Marine. Oh, files. All right. Okay. So if you remember in the build script, what we did is we exported the interface types directly into a Aqua file, and which we called process files Aqua, which is this. And in order for you to efficiently get that, you can basically use this command. We export, that allows you to use Marine to export the interface types, and then you just pipe them into whatever file you want to. And this is what we did there. So if you have a bunch of files, if you have a bunch of interfaces, it's actually pretty efficient to do, and you can script around it and don't ever have to touch anything on that. So on top, you basically in that, so we get the size results now, and on top you have a declaration where we basically name this file process files, and we declare all those ones as exportable. This is wildcard. We could have done it individually, but we did it by wildcard, which basically means it only gets compiled when it's called by another module, which is here. All right, so let's go to the demo real quick, because then things may make more sense. So I'm going to be lazy, and I'm going to use the IPFS desktop, and again, I think it's the command. Hopefully it is. So we wrote a web app, and we can go through it in a minute here. And come on. Okay. So we wrote a web app, and basically what it does, it gets us to a Fluence node. Now, the way we work with IPFS natively, if you will, is the following. We get a Fluence node, and we sidecar the IPFS node. And the communication or the file transfer between the IPFS node and the Fluence node is that basically you get the file by CID from IPFS, and then you transfer it onto the node's local file system. And that allows you now to access that file or that content from your services, which, if you know WebAssembly, is no small feat, because fundamentally, if you look at the fundamentals of WebAssembly, you don't have sockets, and you're highly single threaded, and you are highly sandboxed. And this way, we've provided you, the developers, with a way to punch through some of the sandboxing and safely, through permissioning, access node resources, which includes possibly transferred files from IPFS. So we need to pick a relay. This is just, I mean, there could be any one of them. We got multiple networks up and running, test networks up and running. It's just a small subset of it. And the reason I want to connect first is the following. We sidecar IPFS. So if we want to have a Fluence node work with IPFS node, the way it's set up right now is by pairing over the RPC address, which is here. Okay. So now we can use the IPFS desktop to connect to that particular IPFS node. Oh, look, it works. Yay. It's awesome. Okay, here we get this one peer. We set it up so the IPFS nodes are independent. So it's not a network per se. It's just each one of them. And there are no files there. Okay, so that's cool. So what we want to do is we created the service, right? And now we want to put that service on IPFS. And the reason I use the IPFS desktop is because I can do this and I'm lazy. So I love to do this. And here we go. We get this up. Now, actually, it was already on there. And we get the CID. Now, if we go back here, okay, so what we're doing now is we have a Fluence node and we have an IPFS node. We copied our service, our WebAssembly module, from my local machine onto the IPFS node that's sidecarring the Fluence node. Now we want to get that service deployed on that Fluence node from IPFS. So basically, we have this. This is where the CID is on, and this is the actual CID. And now we deploy the service. Okay, so we deployed a service now onto this particular node with this particular service ID right here, and that should allow us now to calculate various file sizes on the network. Okay. So let's go here. Let's build script. Okay, that's very small. That should work. Let's pull this over here on IPFS. So now any file on IPFS where you have a CID, you can actually calculate the file size using that service you just deployed. All you need to put in is that CID, which I just did. So it's 372 bytes. And you click on get size, and oh, look at that, 372 bytes. By the way, this is also in the examples repo, so you can double check that I'm not bullshitting you. It actually works. It's real. And so now you say, okay, since I'm not seeing the question, I'm asking the questions myself. What's the cool thing about all that? Well, the really cool thing is the following. Everything we've done is through Fluence's Aqua language, which basically gives you a seamless integration over multiple peer-to-peer solutions, including Fluence and IPFS. So you have one single language, one single interface to do peer-to-peer composition across literally 2 different peer-to-peer networks. And that, if you think about it, this is actually quite cool and effective. And so if we look what we did, and this is where, if you have suffered through lib peer-to-peer or any kind of peer-to-peer programming in the past, you really gonna cherish this a lot more than if this is totally new to you. But if you had to do this manually yourself, it would be a major pain in the rear. So this is how we deployed the service, right? So we said we manually copied it onto IPFS. So now we deploy it. So we get our PRID, which is our relay. We get the CID. which we got from obviously deploying onto IPFS. We got the IPFS multi-address. Remember, that's the one, the address I copied for the node we used. And then this is a callback. We call it an error function because Aqua itself is highly functional, but basically it's a callback into your client, whatever the client is. And so basically, we specify the service ID. And then on that relay, we from this IPFS node, we get we use the CID to get the result. And if we get a successful result, we now calculate the module hash. It's basically, so you basically take the WebAssembly module, you hash it, and you get the hash. And from that, we create what's called the blueprint ID. And that's based on the module hash and some additional information for the most part. And this is now what gives us this logical construct of a service ID. So the blueprint ID would be always the same, but if you ran that 10 times or 5 times, whatever many times you want, let's just say K times, you would get one blueprint ID and K different service IDs. All right, I got a question. Okay, we're ending soon. All right, okay. Oh man, all right, I was slower than I thought it was going to be. Okay, any questions on so far on Aqua? Okay, then let me, all right, now I got to power through it. So basically, if we actually want to use that service now, we create the file size, which that WebAssembly module which is deployed, and then again, if you look at it, we just go through it. We get the IPFS references. If it's successful, we get the size. Here is the interface. If success, blah blah blah, and we write it all back into the React application, which I'm not going to go through because I'm going to go back to the presentation and close this thing out, unless you have questions. All right. Just in a nutshell, we used IPFS as a sidecar. We had these bindings using IPFS CLI API to allowing add and get. And we basically were able to move files between Fluence and IPFS for further processing with already deployed services with Aqua. And now I powered into the end. If you want to learn more, there are plenty of resources. Fluence.network. We have a community call every 2 weeks. There's one on Thursday. We got the GitHub. It's github.com/Fluence Labs. We have a YouTube channel, Telegram, Twitter, Discord, all the good stuff. And we are just finishing up a Gitcoin hackathon. We're starting an ETH Global hackathon, I think yesterday. If anybody's interested, I think it's like it's pretty sizable prizes. And also, if you're into peer-to-peer networking, we are hiring. If you're interested in it, and reach out. All right, I have a lot more to say, but that's what I'm going to say for tonight. So thank you for having me. Thank you for being here. If you have any questions now or later, just reach out.
Yeah, thank you so much for presenting. It was super informative. If anyone else has any questions, Bernhard, you should definitely join the Blockchain at Berkeley Discord. I'm not sure if I'm echoing for anyone, but yeah, I posted the link in the chat. And if anyone has any other questions, you guys should just ask him in the BAB Discord.
Awesome. I joined. I'm ready to take your questions. Thank you so much for having me. I hope this was helpful and give you a little bit different perspective on how peer-to-peer can be used in decentralized application building. And if you have any ideas or you want to participate, as I said, we get tons of hackathons coming up. So reach out, stay in touch.